All right, here we go, everyone. Day one. Let's get started and just jump right into some math. So, this first day should be entirely review from previous math classes. Of course, people forget things. You'll see stuff and say, oh, yeah, maybe I saw that once upon a time. That's why we're doing this, is to say, yeah, I learned that before, but I don't exactly quite remember it. Let's get that stuff back into active memory so that you can take advantage of things you've learned before. All right. So we're focusing for this first video on exponential and logarithmic functions, and then the second part we'll look at trigonometric functions. So exponentials. The exponential function family has what is called the base, so that is some number, and then that number is being raised to a variable power. That's what defines an exponential, is that you have some number raised to a variable. This is distinct from power functions, which you'll also see called polynomials, and that is where your variable is the base. So if you have a variable raised to a number, that's a power function, that's a polynomial. If you have a number raised to a variable, that's where you have exponential functions. So that's the distinction between these two things. It's not the end of the world if you say the wrong thing, but for communicating as precisely and accurately as possible, you do want to use the right names for things. A lot of times, just in casual speech, people will say, oh, this thing grows exponentially because they just mean it's huge. But often they're really talking about polynomial relationships, which are not exponential. They are a different family of functions. And so just saying, oh, it's exponential to mean it's huge is very imprecise and you can do better. So do better. Here's a couple graphs of just a few exponential functions. And the one in the middle, the blue curve that's labeled exponent of x, that is our special exponential function that is with a base of e, which we'll revisit very soon. You can see that a feature these functions have in common is they go through the point 0, 1, because any number raised to the 0 power is always 1, with the exception of 0. But we don't do exponentials base 0 because that would be weird and broken and probably dumb. All right. Now, what do these things do? How do they behave? I showed you what the curves look like as a function, but what properties do they have algebraically that we can take advantage of? One of the biggest ones is the multiplication property of exponentials. So this is that if you have two exponential functions with the same base, that's really important, with the same base, then when you multiply those two functions, the exponents add. And this is true for any expression in the exponent. If the exponent itself is some whole function, then the first function times the second function, or the first exponential times the second exponential. What is in the argument of the result is the sum of everything in the exponents of those initial functions. Now, when you take an exponential and raise it to a power, you do not add these numbers, rather you multiply them. So what I've got here, I have a to the x, a is my base, x is the first exponent, and that whole function exponentiated, take that function, raise it to another power. What happens is that you get the base raised to the product of those exponents. So let's see this with some numbers just to check and make sure everything is doing okay. I'll just use base 2 here because powers of 2 are things that I actually have memorized. So that's nice. I'm not saying that you necessarily should. My brain is just full of random junk. So anyway, 2 cubed times 2 squared. So we can just, reduce, simplify everything, do it out the good old fashioned way, and that's totally fine. 2 cubed is 8, 2 squared is 4, 8 times 4, 32, cool. But the sneaky way to do this is to use this multiplication property of exponentials. So they have the same base. That means that when I multiply these functions, I'm going to add the exponents. 2 raised to the 3 plus 2 power, 2 to the 5th, 32. Now, this is actually a little bit faster if you know that 2 to the 5th is 32, which again, maybe you do, maybe you don't. It's not a big deal. But going 2 cubed is 8, and then 2 cubed is 4, and then 8 times 4 is 32, that's just a little bit more laborious than saying 2 cubed, 2 squared, that's 2 to the 5th, it's 32. It saves you one step. So, it's nice occasionally. To show the exponential property here, we have 2 cubed to the 4th power. So that 2 cubed is 8. 8 to the 4th is 64 times 64, which is 4096. But you can also do this by using the exponential property that the exponents multiply when you have an exponent of an exponent. So 2 to the cubed to the 4th power is 2 to the 3 times 4, 2 to the 12th, which is 4096. All right, so that's how these things go. I mentioned the exponential function earlier. This is with an exponential with a base of e. And there are actually several different ways of calculating or really even defining e in mathematics. It's a great number. It's got all sorts of crazy properties. It's one of those magical things that just keeps showing up everywhere, even where you don't expect it. But for the moment, I do want to focus on the property that is arguably the most, or at least one of the most important ones in material science and engineering, which is that the exponential function base e is the function that is its own derivative. And you're like, what does this have to do with material science? What this has to do with material science is that very often we are dealing with phenomena whose rate of change is dependent on the amount of the thing itself. For example, if you are looking at heat transport in a solid, so you've got some insulating material and heat is flowing through it. Well, the amount of heat flow depends on the temperature difference between the two sides of the material. So now we have this rate of change dependent on the function itself. Or if we are looking at concentration gradients in a solution or in some melted metal or anything like that, then the rate of change of the concentration depends on differences in concentration. So that's why this property shows up so much in material problems. And for that reason, most of the exponentials you're going to work with are going to be base E. So it doesn't hurt to know about other bases. Sometimes there are little tricks that you can do to simplify problems, but for the most part, my honest advice is focus on getting really good with base E exponentials because that's going to be where you get the most reward for your effort. All right, so that's exponentials. Bam, done. Logarithms, other side of the coin. This is asking the question, what is the power? Because the exponential was saying, I have some base raised to a variable. The logarithm is asking the question, well, what is that variable? You can define this as the logarithm function being the inverse of the exponential function, which is completely true. So if we have a base raised to a power, and that's why I have b and p here, base and power, you can rearrange this and you can say the power is the log base b of x. Again, I find it helpful to think of it as answering a question. It's how many times do I have to multiply b by itself, because that's what exponentiation is, in order to get x? There are a couple other ways of looking at this too. If you have a different way that makes more sense to you, as long as it's right, absolutely go for it. There's more than one useful and accurate way to conceptualize these relationships. If, on the other hand, you're getting stuck and you're like, oh man, I just can't remember how to do the thing, you can always look at the equations themselves, like literally written down like this, and see which which terms in these equations correspond to each other. Like the b is the base of the exponential, it's also the base of the logarithm. Okay, great. So logarithms undo exponentials. They let us solve for the power rather than solving for the result of raising something to that power. And that's true for logarithms in general, but again, just like you're going to mostly work with exponentials base e, you're mostly going to work with logarithms base e. So much so that when I say log or logarithm, I almost always mean log base e. It's just implied. It's implicit that we're talking about log base e because we're also dealing with exponentials base e. That is not true in all fields. Like in computer science, log base 2 is really important because so much stuff is done in binary. Um, in problems where you have exponentials defined base 10, like the decibel scale for doing sound intensity or for earthquakes, then you're looking at logs base 10 because things are defined with base 10 exponentials. So they are useful occasionally, but the default is logarithm base e unless stated otherwise. Or, unless I forget to say it and then you're like, wasn't something supposed to be? My point here is correct me when I am unclear or when I make mistakes. If something seems like it's been left out, I'm not trying to hide stuff. It's just, it's not possible to speak perfectly 100% of the time. But the intent is logarithm means log base e unless I say log base something. Okay, so properties of logarithms come directly from the fact that they are the inverse of exponentials. So the properties of logs are going to look a lot like the properties of exponentials. The multiplication property, logs convert multiplication into addition. So if you have the log of a product of two things, what you get is the sum of the logs of those two individual things. This corresponds to the property of exponentials, where when you multiply two exponentials, you get the sum of their powers. And likewise, because the logarithm tells you what is the power, you get the sum of the logs when you take the log of a product. Continuing on with that analogy, the logarithm of an exponential takes that power and pulls it out front. So it turns it into a multiplication operation instead of an exponential operation that we get the exponent times the logarithm of the base. Just to show this working in real time, if I'm looking at base 2, again, because knowing powers of 2, log base 2 of 128 is 7. Why? It's because 2 raised to the 7th power is 128. But you can decompose this if you don't have that memorized. You can break it down into smaller chunks to evaluate these things. You can say, okay, well, I can factor 128. I can factor 128 into 4 times 32. So then I'm asking simpler questions. What is the log base 2 of 4? Oh, the log base 2 of 4 is 2 because 2 raised to the power 2 gives me 4. And then what's the log base 2 of 32? Oh, it's 5 because 2 raised to the 5th power is 32. So when you have this kind of more complicated expression, you can use these properties to break them down into smaller expressions that are easier to evaluate. And that's really where a lot of the practical utility comes in to doing these things, is sometimes you can intentionally use logarithms to take ugly expressions and break them down into smaller bits that you can handle better. So that's kind of my pitch for why this stuff is useful, why it matters. But in a direct MSE context, I've already mentioned a couple examples of exponentials. But in thermodynamics, you get logarithms showing up in many different places. I don't want to spoil your whole thermo class for you, but this is essentially what it's going to look like. If you've already taken thermo, then you know. So why do these logarithms show up everywhere in thermodynamics? One of the reasons, not the only reason, is that when you really look at things fundamentally, when you get down to the level of atoms and molecules and you're counting particles and saying, how many states does my system have? How many ways are there to arrange these atoms in a given system? A lot of the thermodynamic properties that we know about, like entropy, uh, are related to logarithms of this state counting idea. More to come in your thermo class. Exponentials are going to show up everywhere in kinetics because, again, rates of change. things moving around, transport happening, how matter moves, how heat moves, and how the driving forces causing the movement of stuff in the physical world are dependent on the amount of stuff present. So that's where a lot of our exponentials come from in kinetics. And just in a more general sense, not talking about any one class in particular, but when we're trying to illustrate and convey and communicate data in material science, there's an interesting challenge that we have to deal with that's not as true in other fields of engineering, which is we span many orders of magnitude. We talk about things all the way as small as electrons and as large as buildings and airplanes and everything in between. uh, when we're talking about material properties, for example, thermal conductivity, electrical conductivity span many orders of magnitude. The difference between the resistivity of an extremely resistive ceramic and extremely conductive metal can be tens of orders of magnitude different from each other. So, like, how do you deal with that? And one of the best ways we have to deal with that is to use logarithms, because the logarithms let us talk about the power rather than the whole value of the entire expression. And that's the kind of thing that you see on a TTT diagram, for example, time temperature transformation. The horizontal axis here, if you look at it, it goes 0, 1, 10, 100, 1,000, 10,000. Those are the powers of 10. This is intrinsically a logarithmic way of displaying the data. And what it lets us do is it lets us see numbers as small as zero point 0.1 and as big as 10,000 on a single axis, which you wouldn't be able to do if you had to show zero point 0.1, zero point 0.2, zero point 0.3, 0.4, 0.5, blah, 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 10,000. Your graph would be a zillion miles wide. It would be useless. All right. I think that's everything I wanted to say about that. I don't want to make these videos over long. The idea is that you sit down and you can watch them in one go and have it be a productive use of your time. So with that, thanks for watching. I'll see you in the next one.